All right, I promised that we'll talk a little bit more about how to approximate this tomato, if the tomato had a speedometer, approximate how fast it was falling after 1 second. And we're going to start by doing that by calculating the average velocity between half a second and 1.5 seconds. Okay, that average velocity will be one way that we can approximate how fast it was falling after 1 second. So what's this average velocity? Remember that the average velocity is going to be the change in position divided by the change in time. Well, between half a second and 1.5 seconds, what's the change in position? It goes from 96 feet to 64 feet. And between those times, how much time has passed? Well, it's going to be 1 second. So we could just do all these calculations out. All right. And we're going to get that we got 32 feet is how far it went in 1 second. And our approximation, is about 32 feet per second. Which I kind of spoiled that. That's actually the answer in this case. It just so happens because of the way the symmetry works in this problem that we actually approximated the actual answer. But in general, in general, you can get a better approximation by making your interval a little bit smaller. If we knew where the tomato was after 0.9 seconds, where the tomato was after 1.1 seconds, we could get a better approximation. And the closer and smaller our interval gets, the better our average velocity will approximate our instantaneous velocity, our speedometer, our tomato speedometer, if you will. Okay? So remember that the rate of change of something is the slope. Anytime you see these two words, these mean the same thing. Rate of change is slope. So the rate of change of an object's position over time is its velocity. Okay? And that's why this average velocity looks like this. And we can see this a little visually. Let's think about and remember how graphs work. Okay? So on our x-axis, we'll have time, and our y-axis will have the height. Well, as time goes on, what is happening? As time goes on, that's as we move to the right. As we move to the right, notice the height is going down. All right? And so we can see this right here, this red curve, is our position function. Our position function. And we just said the slope, the rate of change, the slope of position function is its velocity. So we got this direct tie-in to what we're doing in chapter 2. So what we did in what we're doing when we're finding average rates of change are what are denoted by these secant lines. Okay? Look at this definition down here. If we draw a line between 2 points on a graph, that's known as a secant line. So we have an example here of this blue line, which is just the line drawn between these 2 points. Okay? We have this blue line. This is an example of a secant line. And the slope of this secant line is the average velocity between these 2 points. So the slope of this blue line, slope of blue, that's not how you spell blue. Slope of blue equals average velocity between, I can write my shorthand, between, let's see, blue is this point and this point, so between half a second and 1 second. And then you can see this dotted line, right? This dashed line, rather, is a secant between these 2 points. So similarly, the slope of the dashed line will be the average velocity between 1 second and 1.5 seconds. Now, if again, we have this definition down here. The average velocity of an object is the slope of the secant line through 2 points in the position function. We can find it the way we've been finding it in both of these videos, right? Average velocity is just the rise over run because it's a slope. It's the change in position over the change in time. We've been doing that. Right? So what we want is the instantaneous velocity. Well, what do you think that's going to be visually? Going to be what's known as the slope of the tangent line, which we haven't quite introduced yet. The slope of the line that kind of bounces off the function where x equals 1 at 1 second. Let's do a little exploration of what's going on here. Okay. So we have this visualization. And so here we have a green graph. There's a lot going on here, so just ignore most of this. And let's look at this green graph, this green parabola. Now, let's look at these 2 points. I'm drawing 2 points on this parabola, and I'm connecting them with a red line. This red line is the secant line. Okay? And we can move a point around and notice that the secant line changes. All right? Any point here, the secant line will move. That red line will move. That red line is the secant line. The secant line is just the line between 2 points. You can move both points around again and get a whole bunch of secant lines. Secant lines show the average rate of change. So right here, we have the average rate of change between, I don't know, x equals 0 and x equals 1.2 about. And now as the points get closer and closer together, we're getting the average rate of change over a smaller and smaller interval. And we want the idea of an instantaneous rate of change. Wait, what is instantaneous other than the average over a really small interval? So what we're really going to get into in this whole chapter, what we're really going to get into for finding instantaneous rates of change, instantaneous velocity, is we're really just going to say, well, what happens if these points get really, 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 really close together? In this picture, you can see that as these points are going close together, what is the slope of this red graph doing? As the points get really close together, the slope of this red line seems to be getting flat. Okay? And if we get these things really close together, then really we can find the slope of a function really at any place. The slope of a function is just going to be the slope of a secant line if the points get really, really close together. And that's where we're going in chapter 2. That leads to this concept of a derivative. Okay? And we get some exciting stuff. It's all just rates of change. It's all just secant lines. It's all just slope. If you remember nothing else from this whole class of calculus, what is calculus about? Well, half of calculus is about slope. So this is what we've got, and this is where we're going to go into in the next video with something known as a tangent line, okay? If the secant line, the points in the secant line get really close together, that gives us the equation of a tangent line. Tangent lines will be super important, so stay tuned. You won't want to miss it. I didn't turn off the video. I misclicked. It's hard.